All right. Hello, everyone. Everyone's coming into the Zoom webinar, so I can see the attendees coming in right now. And I will start the introduction as soon as I see the participants number settle down, but welcome everyone. All right. Good afternoon and welcome to today's Winter Science Speaks seminar. My name is Heather Segali, Education and Outreach Director of the UC Davis Tahoe Environmental Research Center. To learn more about TURC, the research we conduct here and around the world, the public education and citizen science programs we provide for the community, and our work with government agencies in the Tahoe Basin and beyond, please visit our website, tahoe.ucdavis.edu. You can also find out how to follow us on social media, how you can participate in our activities, and help support our activities, including these monthly lectures. One of the goals of our seminars is to facilitate dialogue and discussion. We will address questions at the conclusion of today's presentation via the Q&A function on Zoom. The best way to ask questions or make comments is to type them into the Q&A, and our presenter will try to get to as many as possible. Before I introduce today's speaker, I wanted to alert you to a couple upcoming events. April 14th, we have the Living Snow Project with some researchers from the Desert Research Institute. On June 2nd, we have Nature Tells Its Story, the Climate Archive of Caves with Isabel Montañez, and that will be a return to in-person events. And then later in June, we have our Circ-Turk 2, which is our Circumnavigate Lake Tahoe by Kayak with Turk. So I'm going to introduce Dr. Dave Osleger. He is a professor of teaching in the Department of Earth and Planetary Sciences at UC Davis. His research involves the use of sediment and layers to decipher environmental and climatic conditions of the past to provide perspective for understanding modern climate systems. So without further ado, Dr. Osleger, welcome, and thank you very much for taking the time to present to us.
Thank you for that, Heather. I'm happy to be here today. The thing about Lake Tahoe is that it acts as a bathtub. It acts as a basin for capturing sediments that get washed in off of the surrounding watershed. So you know as well that the Tahoe Basin is composed of a very narrow shelf with a steep drop off into the deeper water of the deep basin. The total depth here in the middle, I hope you can see my cursor. The greatest depth here in the bottom of the basin is around 500 meters, somewhere around 1,600 feet. And Tahoe acts as a recorder of events that occur in the watershed surrounding the basin itself. So it's a little bit like the motto for Las Vegas. What happens, what sediment enters the lake remains in the lake. And the sediment that accumulates at the bottom of Lake Tahoe is kind of like a record of all the different climatic and even seismic events that have occurred in the surrounding watershed. So what we're going to talk about today is how we can use those sediments at the bottom of Lake Tahoe to say something about past changes in climate in the Sierra Nevada. Okay. So let's start by defining a few terms. You'll understand intuitively that sediment are loose particles of sand, silt, and clay, gravel that get washed into a body of water from a stream or a glacier. In this case, this is sediment being washed into the lake from the upper Truckee River. And what happens is the sediment is created by weathering and erosion from the surrounding mountains. That solid rock of the mountains gets broken down into small particles of sand, silt, and clay. Sand are just rounded grains like you find on a beach. Clay is like that very fine grained material that you feel with your hands when you're creating a pot. And silt is just that in-between size of particle. So these grains of sand are carried downstream in rivers or glacial meltwater or snow melt runoff. They enter a body of water like an open ocean, or in this case, the lake. They get dispersed by wind-driven waves, and eventually that sediment settles out to the bottom of the lake very slowly. We call that process deposition. So sediment is derived from the erosion of the surrounding watershed. It gets deposited on the lake and accumulates on the shelf, the slope, and the deep lake basin in Tahoe. This has been occurring continuously, relatively continuously, over the entire 2 to 3 million year history of Lake Tahoe, which I'll allude to in just a short while. So, how much sediment fills the bottom of Lake Tahoe? This is a question we don't really have an answer for. We do have estimates, and the best estimate that we have is about 1,300 feet of sediment, about 400 meters. And the way we know this is by using a technique called seismic reflection profiling. So what happens is a ship goes out onto the lake and it'll sail along a traverse, in this case from N to M. Here's M and here's N over here. And they'll release sound waves using a device that creates a sound wave. And that sound wave penetrates from the surface of the lake down through the water and then bounces off the lake floor back up to that boat. And there are sensitive microphones trailed along on a cable behind that boat that record those echoes. You know this is sonar, right? You've all heard the ping from submarines in old World War II movies. This is the same sort of thing, except the sound source is powerful enough to penetrate down through the body of the lake water and down into the sediment below the surface. When that sound wave hits an interface between one layer and the next layer, it bounces back up to the surface where it's recorded by those hydrophones. And the time it takes for that sound wave to be released from the boat down to that sediment layer and back up to the surface is a measure of the distance. And so we use these seismic surveys to sort of create this ghostly image of the sediment, the arrangement of sediment beneath the surface below the lake floor. So on this scale here, this is water depth in meters, 300 meters, and then this is in seconds, essentially the time it takes your sound waves to bounce off that surface down beneath the lake floor and then bounce back up to the ship. And so what we have here is about 400 meters, about 1,300 feet of water depth using this scale in this particular location from M to N. And we have at least 300 meters, about 1,000 feet of sediment beneath the lake floor. So we don't really know exactly how much sediment is in the bottom of Lake Tahoe. These surveys, these seismic surveys are from fairly long ago in the 1970s, and they were able to penetrate relatively deeply, but not as deep as we would like to be able to see the true rock floor beneath the sediment. But the best estimates are about 1,300 feet of sediment and about 400 meters. So this is a cartoon, but it shows, and it's not really very realistic, but it shows the various components of what we're talking about here in this discussion of ours. It shows the Sierra Nevada on the west, the Carson Range on the east. You know, they're composed of granitic rock that formed long ago. It's about 100 million year old rock. The mountains, by the way, are much, much, much younger than the rock itself. The rock is 100 million years old. The Sierra Nevada are somewhere less than 5 million years old. And the lake basin itself is about 2 to 3 million years old. So the lake basin was formed by downfaulting. These slabs of rock slide downward along faults, just kind of like books stacked on end. So think of books on a bookshelf with a bookend here and a bookend here. And one book ends the Sierra Nevada, another book ends the Carson Range, and then tilt those books to the side. And what happens? They kind of slide down along the covers relative to one another. And you create sort of a low area where the books have all slid down along those faults. That's the basin that we're forming by that faulting mechanism. And so at the very bottom, the very base of the lake are fault blocks, we call them, of granite rock. Above that is maybe 1,500, 1,300 feet of sediment. That's the stuff we're interested in today's talk. And then above that is somewhere about 1,000 to 1,600 feet of water. Okay. The other thing we could pull from this is that, from this particular diagram, is that this also shows the extent and east-west profile of the nature of the watershed. So storm runoff or snowmelt from this side of the Sierra and crest will flow downstreams and into the lake. Any kind of storm runoff or snowmelt on this side, on the west side of the Sierra and crest, will flow down the west side into the American River, the Rubicon, the Yuba, et cetera, and then down into the Central Valley of California. So our watershed extends from the crest of the Sierra to the crest of the Carson Range. Okay. So this is interesting. By the way, what I wanted to show you here is that the sediment at the bottom of Lake Tahoe is essentially the same elevation as the surface of the Carson Valley just off to the east. And so this is a very interesting figure that shows us the Tahoe Basin here. North is over here to the right, relative to the Carson Valley and the Washoe Valley, and then the valley where Reno is located over here to the northeast. And the only real difference between Lake Tahoe and the Carson Valley and Washoe Valley is that the Tahoe Valley, the Tahoe Basin, has been blocked off by volcanism at its north end. And so up here to the north, here's the Truckee River up here near Truckee. This is Mount Pluto and North Star and all the mountains north of Lake Tahoe. That volcanism is about 2 to 3 million years old. And that volcanism is what shut off the north end of the Tahoe Basin, so that water could accumulate within that low area and build up to become the lake as we know it today. That's really the only difference between the Tahoe Basin and Carson Valley or the Washoe Valley, is that the volcanism beginning around 2 to 3 million years ago, combined with that down dropping along those faults, that's what created the Tahoe Basin. Now, the other interesting aspect of this is that this basin creation in which Tahoe formed was coincident with the so-called ice ages. And we've been in an ice age that I'll show you more detail on in just a second, for the past 2 or 3 million years, specifically about 2.5 million years. We've been in an ice age. And I'll show you what I mean by that very shortly. And so 1,300 feet of sediment in the bottom of Lake Tahoe represents about 2 to 3 million years of sediment deposition or accumulation at the bottom of the lake. Okay, what influence does glaciers have on the input of sediment to Lake Tahoe? So the map shows the extent of the glacial ice cap that crowned the crest of the Sierra during the so-called last glacial maximum, the age of the timing of when the glaciers were at their maximum extent most recently was about 20,000 years ago. And ice about 2,000 feet thick or so covered the crest of the Sierra, extending all the way down from the Sequoia Kings Canyon area all the way up past, here's Tahoe right here, of course, all the way up into the Lost Sierra up to the north of us. Geologists have recognized 3 distinct phases of glaciation by reading different aspects of the landscape. The most recent one is about 15 to 25,000 years ago. We call that the Tioga glaciation, named for Tioga Pass in Yosemite Valley, or in Yosemite National Park. The next oldest is called the Tahoe glaciation. That's about 65 to 140,000 years ago. And then the oldest one that we could recognize is called the Donner Lake glaciation. That's about 400 to 600,000 years ago. And so the idea here is that by reading different features in the landscape that I'll show you in just a second, we can determine when glaciers were at their maximum in the Tahoe Basin, sculpting and carving the terrain of the watershed surrounding the lake and creating sediment that gets deposited within the lake itself. Okay, Glaciers 101. This is the Athabasca Glacier in the Canadian Rockies. And it's in a state of retreat right now, as most glaciers are worldwide due to a warming planet. And what glaciers are is they originate up here in the highest elevations where snow accumulates over centuries to millennia, eventually compacts to create glacial ice. And under its own weight, the ice moves down slope by gravity. The weight of the ice is enough to allow it to slowly but surely move down slope. It's sort of a river of ice. Now, as it's moving down slope, it's carving into the adjacent rock through which it's traveling. So it's abrading that rock, it's quarrying that rock, it's pulling rock away from the walls, and it's resculpting that valley through which that glacier is flowing. When the glaciers transport massive amounts of sediment on top of the glacier, within the body of the glacier, and along the flanks of the glacier, as well as at the toe of the glacier, the snout of the glacier, as it's bulldozing its way down slope. So when glaciers start to melt during warmer phases of Earth's climate, they start to retract, and all that sediment, house-sized boulders, gravel, cobbles, sand, silt, clay, that all gets dumped out of the icy matrix and gets left behind. So what we see as glaciers retreat are elongate ridges of glacial debris that we call lateral moraines, like this right here. I'll show you some of these in the Tahoe Basin in just a second. And this pile of sediment over here spilling out between the rocky walls and the glacial ice itself. And as the glacier melts and recedes, it commonly forms a meltwater pond down here near the toe and meltwater streams. And those meltwater streams transport some of that sediment down here into the region just past the nose of the glacier. We call that outwash. So here's another image of a retreating glacier. This is called the Nisqually Glacier. This is on Mount Rainier. So here's the crest of Mount Rainier up here, and here's the Nisqually Glacier coming down through this rocky valley. And here's where the nose of the glacier is today, but it used to be all the way down here past the edge of the photograph. And as it's retreated over the past several decades, all of this sediment, these cobbles and boulders and sand and clay have been released from the body of that glacier, and they accumulate in the valley where the glacier used to be. We call that glacial till, and that's the material that makes up lateral moraines. That's the stuff that makes up outwash. Glacial till is just that general term for these deposits of poorly sorted, irregular sedimentary debris left behind by a melting glacier. This is happening everywhere today. As glaciers go into retreat, sediment is being released, and all that sediment is being washed down slope by the meltwater from those melting glaciers. So you may ask yourself, how do geologists recognize past glaciations on the landscape? And we do that by some very straightforward, simple observations. Fundamentally, what we do is we go to modern glaciated terrains and look how modern glaciers work, whether it's Switzerland or Alaska or the Chilean Andes. And we sort of try to understand the processes involved in modern glaciers, and then try to project those back in time to understand the remnants left behind after glaciers melt and are long gone. So one of the things we look for are piles of debris like this. This is glacial till, just like I showed you. And you can see there are a bunch of boulders mantling the very top of this pile. There's sand, there's cobbles, there's gravel. It's just a massive dump of sediment. And that is very characteristic of how glaciers release their entrained debris that they've eroded from the surrounding mountains and then transported down slope in the body of that glacier and then left behind as they melt and retreat. We also look for things like gigantic isolated boulders like this. This is called a glacial erratic. Many of you have seen these. Many of you know what they look like. They're all over the place. These are large boulders that have been moved along in the body of ice. When the ice melts, that boulder gets dropped out in the meltwater. It gets left behind. And you may say, well, why can't this just be an erosional remnant of the underlying granite? Well, typically, these bodies, these boulders of the erratics are a totally different rock type than the underlying rock on which they're deposited. So we know that they came, and we could backtrack to find the source for this body of rock. And many of them are miles upslope. So we know they were deposited and left behind by glaciers. Another feature that we use to identify the presence of past glaciers are U-shaped valleys. Now here in the northwestern corner of the lake, and this is a Google Earth image, of course, we have Blackwood Canyon and Ward Canyon. Here's the Bear Creek Canyon where incline is, and Olympic Valley, of course. And the arrows are showing the downslope movement of glaciers through each of those glaciated valleys. Now the ice originated up here in this big bowl at the head of Blackwood Canyon, in these big bowls back up in here at the head of Ward Canyon, back up in here in the incline area, and back up in here in Olympic Valley, where you see those very sharp edges. Those are the places where the glacial ice was attached to the rock. And as the glacial ice tried to move down slope, it pulled off, it quarried large slabs of rock. When you go skiing and you drop off a very steep slope, you're kind of coming off the head wall of where that glacier used to be. And as the ice moves down slope through any of these valleys, it follows stream valleys. Now, stream valleys, when streams incise into rock, they tend to carve V-shaped valleys. But as glaciers move through those V-shaped valleys, they abrade and carve away at the rock, turning a V-shaped stream valley into a U-shaped glacial valley. And so that's the characteristic that you see in all of these. There's a U shape here in the Ward Creek drainage. There's a broad U shape here in the Blackwood Creek drainage. If we move further to the south, here's Mckinney Creek, General Creek, Meeks Creek. You see how these broad U-shaped valleys have been molded and sculpted by the motion of glaciers. The glaciers originated up here in the Sierra Crest and moved their way down slope, transporting all kinds of eroded sedimentary debris down toward the shore of the lake. When the glaciers melt and retreat back upslope, those meltwater streams like Meeks Creek and General Creek and Mckinney Creek transport the precursors of those modern streams, transport all that sedimentary debris from the glacier downslope and into the lake. This is where most of the sediment in the lake is coming from. It's coming from the meltwater streams, transporting that glacial debris downslope and then depositing it in the lake basin underwater. You can also see here in between each of these glacial valleys, these elongate ridges, these are lateral moraines, LM, lateral moraines. And these are composed of glacial debris like that glacial till that I showed you earlier, these random assortments, these dumps of boulders and cobbles and sand grains. And so all a moraine is a ridge of debris that separates one glacial valley from another glacial valley. And then as we move even further south, we see the sort of classic terrain of Fallen Leaf Lake and Cascade Lake, Emerald Bay. The glaciers all headed originated up here in the high country of the Sierra Desolation Wilderness area. That's where the ice was at its most thick. And then tongues of glaciers migrated downslope toward the low areas where the lake basin is. And as they moved downslope, they carved out the basin that is Fallen Leaf Lake, the valley here toward Baldwin Beach, Cascade Lake, and Emerald Bay, of course. In between, they left behind lateral moraines that we drive across all the time, separating each of those glacial valleys. So the evidence for past glaciation is all around us. You just have to be able to read the landscape, as do geologists, to try and understand those sort of specifics and the dynamics of how glaciers carve the landscape that we all enjoy. So maybe the bottom line here for all this is that as glaciers grow and expand downslope, they erode the surrounding rock and they create sediment. As glaciers melt and retreat back upslope, that sediment gets transported downslope by meltwater streams and gets deposited in the lake itself. So glaciers add immeasurably to that 1,300 feet of sediment below the lake floor within Tahoe. In fact, they're probably the dominant mechanism for how sediment reaches the lake basin. Let's say something about the ice ages and how we use sediment to determine climates of the past. And to do this, we're going to go to the world's oceans. Now, back in the 60s and 70s and up through today, we have a research program of ocean-going vessels that have drilling rigs attached to them. And we drill cores down into the bottom of the ocean floor. And these cores, when we bring them back up to shipboard, are typically around maybe 6 inches across and maybe even up to a mile deep. And they're basically sediment and rock below the ocean floor in a large column that we cut into slices. We cut it in half. Half of the core is used for sampling. The other half is stored in repositories worldwide. And we've put thousands of holes down into the seafloor, and that has told us massive amounts about our planet and how it operates. For our purposes, for climate purposes, the most interesting component within the sediment are these little guys. These guys are much, much, much smaller than a grain of sand. These are called foraminifera. These are amoeboid animals that live on the ocean floor. And the key thing is they precipitate their shells out of a mineral called calcite. And the chemical formula for calcite is just calcium, carbon, and 3 oxygens. And here's the key. When they precipitate that shell as a protective outer coating around the soft little blob of goo that is the animal, they precipitate it in chemical equilibrium with the water in which they're living. And the chemistry of their shells can be used to tease out the temperature of the water in which that organism lived. So if we look at thousands of foraminifera shells downward in that core, they tell us something about ocean temperatures back through time. So let me demonstrate to you what the bottom line end result of all this is. Now this plot, it was created by the geochemical evidence from literally tens of thousands of foraminifera brought up in cores from the world ocean, from seafloors all around the planet, and then integrated. The chemistry of those foraminifera tell us when the oceans were warm, when the oceans were cooler. And so this plot was created. On the vertical is time in millions of years. So 500,000 years ago, 1 million years ago, 2 million years ago. Along the horizontal is something called oxygen isotope value. That's detail that doesn't matter. More importantly, it tells us when the oceans were cold over here on the left and when the oceans were warm over here on the right. So today we live in a warm interglacial climate phase. We call that the Holocene. And what you see going back over the past 2 million years are alternations in glacial, interglacial, glacial, interglacial cycles. So at times the planet became colder and glaciers grew and expanded. Then they would alternate with times when the planet grew warmer and the glaciers melted and contracted. And there were about 20 or 30 of these over the past 2 million years. The most recent glaciation, the Tioga, was about 20,000 years ago. That's the most recent one here in the Tahoe region that we could recognize. Prior to that is the Tahoe glaciation about 70,000 years ago. And that's this one right here. But between the Tahoe and the Tioga, there was a warm interglacial phase. Then the oldest one we could recognize is the Donner Lake glaciation. But there were 2 glaciations and 2 interglaciations in between the Donner Lake and the Tahoe. There's no evidence of that. The problem is when glaciers move down through a landscape, they basically erase most evidence from previous glaciations. And so we only see the remnants of the most recent glacial events. We have no evidence of these 2 glaciations or any of these older glaciations that invariably, undoubtedly, influenced the sculpting of the landscape in the Tahoe Basin and the creation and deposition of sediment within the Lake Tahoe Basin. So we tend to think of the ice ages as being the sort of monolithic cold phase in Earth history. Well, it's more complicated than that. And we know this by exploring the world's oceans. We know that the ice ages, there were several, 20 to 30 actual ice ages interspersed with warmer interglacial phases. This is how we need to view the ice ages. Today, up here at the very tail end of the plot, we are looking at a warmer interglacial phase. That's what we're in right now. And I'll show you greater detail on that in just a second. Okay. So the reason for showing you all this is to get you to realize that it's more complicated than just, oh, 3 glaciations, Tioga, Tahoe, Donner Lake. And that's what sculpted our landscape here in the Tahoe region. Oh, and that's what created the sediment that went into the bottom of the lake. Well, it's more complicated than that. Most of the sediment in the bottom of Lake Tahoe is 2 to 3 million years in age, and most of it was generated by the coming and going of ice age glaciations multiple times, many more than we could actually recognize in our own region. Each of those glaciers, when they moved down slope and then retracted, acted like a saw blade, cutting into the landscape, carving those U-shaped valleys deeper and deeper and building those lateral moraines up higher and higher. This is the way that mountainous landscapes in the American West were formed, whether it's Yosemite or the Colorado Rockies, Montana, you name it. It's all happening in the same way throughout the entire American West. And what I'm showing you here is glacial debris. This is all runoff sediment that was transported by the retreating glacier up here, carried down through the stream valley, and ultimately, during floods, that sediment will all be transported further down slope and dumped in some sort of basin like Lake Tahoe. So this is a plot of temperature on the vertical in degrees Celsius. So this is 0 is plus or minus today. This is -1 degree C, -2 degrees C, -3 degrees C, -4 degrees C, or about -7 degrees Fahrenheit. Along the horizontal is time. 22,000 years ago, 20,000 years ago, 12,000 years ago, and this is today. Along this vertical is positive temperatures, roughly today, 1 degree C warmer, 2 degrees C warmer, and so on. So this is a plot of past temperature relative to today versus time. So here's our last glacial maximum, the Tahoe glaciation. The planet globally, not just our region, but globally, was on average about 3 to 4 degrees C, about 6 to 7 degrees F, colder than it is today. And that was enough for glaciers to grow over the entire northern reaches of our planet, and including Antarctica in the southern hemisphere. Since then, natural climate variability has caused the planet to warm. And as it warmed, those glaciers melted. Here's our warming that we can document in many, many, many different ways to create this figure. Here's our planet warming. 16,000, 14,000 years ago, we had a cold snap in here. And then around 12,000 years ago, we entered a warm interglacial phase that we're still in today. We call that the Holocene. And through the Holocene, temperatures have been remarkably stable, varying only about 1 or maybe half a degree up or down from an average. And it's no accident that during that long phase of warm, stable, equable global temperatures, that agriculture originated about 10,000 years ago. And then about 5,000 years ago, the origins of civilization. This is the Egyptian and the Sumerian cultures that eventually were spread worldwide. The East Chinese, the Andean cultures throughout the Americas and throughout the entire world. This is the advent of what we would call history. All this is happening during this nice, warm, interglacial phase of global climate. When we get here to the end, instrumental records from many, many, many sources tell us that the planet is warming rapidly, and you all know why. That turnaround right there is the Industrial Revolution of the mid-19th century. And this is our current warming planet right here in red. And then the dashed line is our projection up to the year 2100. So whether this works out or not, nobody really knows for sure. But if we take the current rapid increase in the rate of global warming and project it upward over time, this is the rate at which our planet's going to warm faster by a magnitude, by an order of 10 than any other time of global warming in Earth's past. So we all know the signature here. We all know that the Industrial Revolution was the beginning of the use of fossil fuels and the return of carbon back into the atmosphere, from which it was stored deep underground as coal or oil or natural gas. We also know that's coincident with an increase in population since the Industrial Revolution. This is what we have, this is what we're dealing with right now. And the real reason we know this is human induced, is that the rate of temperature increase is so much faster than anything that's ever happened naturally in Earth's past. I know I've just induced climate anxiety in you, and I apologize for that. Let's save this issue for another day. Okay, what I'm going to do in the last 10, 15 minutes of this talk is discuss a little research that I did. I'm going to summarize it very briefly. It's some research I did with some colleagues a few years ago. And the question we're answering is, how does sediment enter the lake over the last few thousand years? And what can that tell us about past climate changes recorded within sediment cores? So my colleagues and I collected cores from the north end of the lake here and the south end of the lake here. And they're only about 5.5 feet long or so. They're not really very extensive, but they reach back for 7,000 years. And we do all kind of analyses on these things. We're geologists, so we use all the technology we have at our disposal to measure the mean particle size. This is depth in centimeters. So 160, 170 centimeters is about 5.5 feet. And we measure particle size. It ranges from silt to very fine sand to coarse sand. We measure the magnetic properties of the sediment. We measure the organic carbon, and we do some geochemical measurements, the carbon isotopes and the carbon nitrogen ratios for productivity, of the biota of the watershed. I'm not going to get into that today, of course. These numbers over here are dates. So at the bottom of this core is a volcanic ash. And we know that volcanic ash has an age of about 7,000 years because we could chemically fingerprint it to an eruption in the Crater Lake area of Southern Oregon that happened 7,000 years ago. Now, what happened is the precursor to Crater Lake, a volcano called Mount Mazama, erupted. The ash gets blown into the atmosphere. It gets carried downwind. It settles out over top of, it blankets basically the entire Western US, including the surface of Lake Tahoe. Lake Tahoe would have been a horrible, horrible place to be 7,000 years ago when that ash came down and covered the entire surface of the lake. Slowly but surely over time, that ash settled out through the water column all the way to the very bottom of the lake, where it formed a layer about ½ an inch thick, about 1 centimeter thick. And that's what we're recording, that's what we're capturing within our cores. So we know that about 5.5 feet of sediment has accumulated in the past 7,000 years in the bottom of Lake Tahoe. Okay. These other numbers are radiocarbon dates. So we find things like pine needles and charcoal, organic matter within the cores, and we analyze those for the date when they died. And so they provide sort of checkpoints, age control for different points within that core. So here's ages of around 5,400 years before the present, 3,100 years, 1,450 years ago. And they tell us what's happening when. We would love to have more radiocarbon dates, and that's probably the greatest weakness of this entire project. But it does give us some dates on which to hang different climatic events. So thinking about what the sediment is telling us, this is a portion of the south core, and this is just mean particle size. And those round circles there are different samples every centimeter downward through the core. And so this is a course, and this is an X-ray or X-radiograph of the core, by the way. It's kind of hard to interpret, but it gives us greater detail. So this is coarse silt. This is very fine sand. This is a coarser interval, coarser, finer, coarser, finer, coarser, finer, and so on. The fine-grained stuff looks like this. This is a scanning electron photograph of that sediment. And what it shows are fine grains of silt. These are flakes of mica, biotite, and muscovite, little tiny flakes of minerals that sort of float in the water column on their way down to the bottom. And these fragments, these little hair curlers here, and these sort of fragments here and this fragment here, those are diatoms. And diatoms are floating plants that live in the surface of the lake. They grow shells around their bodies made of silica, and that protects them from being eaten by zooplankton, these floating animals that feed on the floating plants. And when the diatoms die, their shells fall to the bottom of the lake, and they accumulate on the lake floor. So the process here is called suspension settling. So the surface waters of the lake have clays in them. They're wind blown in. Maybe they're coming out from rivers and streams and then floating along the surface. They're diatoms in the surface waters. They all eventually settle out very, very, very slowly down to the lake bed. These coarser intervals right here look like this. And you notice the scale is 5 times here what it is in the uppermost image. And these are fragments of quartz and feldspar. Those are grains of sand coming from the surrounding rocks of the basin. And this big round thing here, that's a larger diatom shell. We interpret these as being as a type of deposit called a turbidite. Now, a turbidite is essentially a geologically instantaneous event. And what happens is during intense runoff from storms, the streams and rivers, 63 streams draining into Lake Tahoe, carry that sediment in the stream runoff down across the landscape. When they hit the shoreline of the lake, that water and that sediment gets funneled into these deep canyons carved into the steep margins of Tahoe. This canyon here, this canyon here, this canyon here. And that constrains the flow to a very narrow slot on the margins of the lake. And that slurry of sediment-rich cold water gets funneled down through those canyons. And when it hits the open edge of the lake, it fans out and forms these deposits, these lobe-shaped fans of what are called turbidites. And those are typically the coarser grains, the sand grains. The finer grains get kicked up in a turbulent cloud, and they get carried out here into the deeper basin shown here in purple. And that's where the clays tend to settle out in the deeper parts, the quieter parts of the lake basin. So turbidites are basically instantaneous events that typically reflect an intense storm in the watershed. So, you know, I'm not sure this is gonna work, gang. No, you know, I had a video here, a really nice video to show you what a turbidite looks like. This is the URL for it if you want to go and watch it. Technology, it doesn't always work, does it? But these are stills from the video I was going to show, and these are experimental turbidites. Basically, geologists create a narrow slot of plexiglass, and they pour a slurry of sediment and water into another body of water and watch how it moves down slope to recreate what are called turbidites. And eventually, when that cloud of sand and clay settles out, the coarser sand grains settle to the bottom, then the finer clays settle out on top, and they form a little couplet of sand clay. So in places where turbidites build up, you get a sand clay, sand clay, sand clay, sand clay, sand clay alternation. And those tell us that these are deposited by turbidity currents, a very, very common mode of deposition within basins like Lake Tahoe. And a third way that sediment can be deposited within the lake is by very abrupt catastrophic events like the McKinney Bay landslide. So here's McKinney Bay over here, and here's the big scar left behind. Many of you have already heard all about this event. It's been dated to somewhere between about 12,000 and 21,000 years ago. Very challenging to date these types of deposits, but using some very clever geological detective work, other geologists have determined an age of about 12 to 21,000 years ago for this McKinney Bay mega landslide, probably triggered by movement along the West Tahoe Dollar Point fault zone that lines the very edge of the lake right in here where my cursor is. Actually, it goes up through here. I'm sorry, right through here is Dollar Point, and it goes right up through here. When that earthquake occurred, the entire wall of the basin was let loose. It cascaded very abruptly and violently down here into the bottom of the lake. That's all those big bumps and irregularities. Some are a mile across and 400 feet high. These are gigantic blocks of the walls of Lake Tahoe that very abruptly and catastrophically were dumped into the lake. The story is that it kicked up a tsunami that washed back and forth in the lake. It's a very interesting story, and somebody could tell you that story much better than I can, specifically the geologist who came up with that story in the first place. So 3 different ways sediment enters the lake: by slow suspension settling of fine particles, by rapid deposition from turbidity currents, and by catastrophic deposition from mega landslides. So I'm coming close to the end of my time, but what I'm going to do is I'm going to wrap this up very, very, very quickly. Okay, so give me 2 minutes, 3 minutes, and I'll wrap this up. So what I tried to do using the core data of sediment that we had was try to equate events in the Tahoe sediment record with those of closed basin lakes in the adjacent Great Basin, Pyramid Lake, Walker Lake, Mono Lake, and Owens Lake, and with what's happening in the California Delta here. So you know that when snow accumulates on the Sierra Crest, it flows eastward down into Tahoe and down into these closed basin lakes in the Great Basin, Owens Lake and Mono Lake and such. And snowmelt over here on the west side of the Sierra Crest flows down all the rivers, draining the west side of the Sierra, and ultimately meets the Sacramento and San Joaquin rivers that merge here in the so-called Delta. So the idea was during wetter phases, we'd get more turbidites in Tahoe. We'd get higher water levels in these Great Basin lakes because of the excess water, and we'd get increased freshwater flow in the Delta. And the way we know that is by drilling cores into the Delta and then analyzing the pollen of plants that once lived there. So some plants are more freshwater tolerant, some plants are more brackish water tolerant. And so during drier phases, we'd get fewer turbidites in the Tahoe Basin, lower water levels in Great Basin lakes, and increased salinity in the Delta. So we came up with this figure that shows us before about, these are the two cores. This is the Tahoe Basin, the Western Great Basin lakes, the San Francisco Bay Estuary. Before about 5,600 years, Tahoe has a low turbidite frequency. It's also characterized by intense aridity and a low stand in Pyramid Lake, meaning drainage from Lake Tahoe down into Pyramid Lake was at a minimum. Between about 5,600 and 3,100 years before present, Tahoe has a high frequency of turbidites, meaning in lots of intense storms. We had high stands in all these Great Basin lakes, and we had increased freshwater plant life within the Delta, meaning the fresh water was flushing down off the Sierra and pushing that saline water back out towards San Francisco Bay. There was sort of a gradient between the freshwater push from the Sierra pushing back against the tidal flow of saline water coming up through the Golden Gate. And then between about 3,100 years and 900 years, we get dry conditions in lake low stands. We get buried tree stumps within the Tahoe watershed, within Lake Tahoe. We get low stands in Pyramid and Walker Lake, and we get increased salinity in the Delta. So it's a gross scale of times of increased precipitation and increased drought, but considering the amount of radiocarbon dates that we have that we were able to attain, this is kind of the best we can do. I wish we could give a year to year, a decade to decade type of record of precipitation and drought, but Tahoe just does not preserve those kinds of high resolution, high precision sediment records. It is what it is. Summarize very quickly, just two more images after this. I'll answer some questions. The majority of sediment filling the Tahoe Basin is created by the glacial interglacial cycles of the ice ages in which we live. During the Holocene, we get deposition from suspension settling, turbidity currents, underwater landslides. And then the sediment patterns allowed us to tease out long-term millennial scale, 1,000-year scale phases of increased aridity and increased precipitation, with the goal being ultimately to find that place where we can get a higher resolution record of climate events in the Tahoe Basin and the Sierra as a whole. Finally, why do you care? You know, why are you here at this talk? I mean, honestly, why are you watching this? Why is this relevant to you? And the answer is to be sort of broad about it, is that understanding the origin of the landscapes around us gives us a deeper appreciation for our environment. When you go hiking, when you go skiing, you look around, you understand a little bit about what glaciers do to carve our landscape, and maybe have a sort of a visualization of what's happening beneath the surface under the lake, under that gigantic body of blue water. Just have a deeper understanding, a deeper appreciation of the world around you. And the second, sort of more technical relevancy of this talk is that identifying natural climate variability of the past gives us greater insight, sort of a baseline for comparison with modern human-induced climate change that we're all experiencing right now. And then it would be remiss of me to not take this opportunity to do a very shameless plug for a book that some of you may be interested in. This is a book I just published recently, Geology and Landscapes of America's National Parks. It just came out this past December. It's available for purchase if you're so interested. It's a textbook, gang. So, you know, I tried to write it for a general audience, but it's a textbook, right? Hopefully people will use it. If you're at all interested, please take some time to look it up and have a look. The end. Heather, take over.
Great, that was excellent. So if you want to stop sharing, we can go to the Q&A here.
Sure.
We have 7 questions. One was from early on from William Coleman. The question was the Cascade Range not glaciated?
Say that one, I'm sorry, one more time, Heather.
So around 12:14 of your presentation, he asked, so the Cascade Range was not glaciated?
The
So
Cascade,
said, yeah.
The Cascade Range. Yeah, actually the higher parts of the Cascade Range were glaciated, but only in isolated spots. Mount Lassen or Lassen Peak to the north was glaciated, and Shasta to the north of Lassen was also glaciated. In fact, Shasta still has glaciers radiating outward from the very crest of the peak of Shasta, even today, of course. So yes, the Northern Sierra and parts of the Klamath, the Castle Crags and parts of the Klamath Mountains were glaciated as well, but they were more sort of localized ice fields rather than broader elongate ice caps like that crown the Sierra.
Okay, and then Hannah has a question. Will glaciers come back? Under what scenario and timeline? If humans go extinct and stop our damaging practices, what will the Earth's healing look like, especially regarding glaciers? And without artificial warming, you know, what is predicted possible in the next thousands of years?
Yeah, that's a really great question. When I showed you that plot of the interglacial glacial variations, you see that we're kind of at the peak of a warm interglacial now. And if humans weren't around, it's almost invariable that we would return to another renewed glaciation. That's just the way the climate system works on the planet today. Whether this is good or not, I'm not quite sure, because New York City was under 1,000 feet of ice. So this may not be the best thing to return to a glacial phase for our planet. But what's happening now is that humans are creating something called a super interglacial. We may be staving off the next glacial phase because of this abrupt pulse of warming that we're contributing to right now. So the future is a little bit indeterminate. Without humans, it's almost inevitable that we would return to a glaciated world. With us around, we're kind of sending ourselves in the opposite direction. The pendulum swinging a bit too rapidly toward an overly warming planet.
All right, we have 2 questions about the sediment layers. If we look through the layers of sediment, what evidence might we see of the whole-scale logging and denuding that occurred? And how does that affect Lake Tahoe today? And then also, what factors were taken into consideration when determining the location of the cores, where they were taken from?
Right, right. So one of my colleagues on this project, whose name escapes me now, I apologize. He's a lovely, wonderful guy. He did his dissertation down at UC Davis with Charles Goldman, who you all know, on the effects of logging in the Tahoe Basin. And he was able to use some very high precision dating to show that during the
Alan Havert.
Yeah,
Alan Havert.
Alan Havert. Thank you very much, Heather. Yeah, I should not forget Alan's name. He's a lovely guy. He determined that the logging operations basically allowed soils to be washed off the Carson Range primarily and down into the lake basin. So at the very, very tops of our cores would be a gigantic pulse of sediment derived from those logging operations. And he was able to show this very, very clearly in his dissertation. Where the cores were chosen was determined by Alan. He tried to aim for 2 deep water points where we wouldn't be too close to the margins. We'd get sort of a biased record of sediment coming in from one particular source. Down in the deepest part of the basin, you want the quietest water where you get the highest resolution record of events. And a bit's arbitrary. You know, I think all of us, or many of geologists, would love to have many, many more cores and deeper cores. But quite frankly, nobody, including myself, wants to see a drill rig floating out on Lake Tahoe. That's not going to happen. And I fully agree with that. It's a little bit arbitrary to answer your question as to where we put the location of cores.
Okay. So William Coleman actually says he wrote Cascade Range, but actually meant Carson Range. So the question was, did the Carson Range have glaciation?
Yeah. So did the Carson Range have glaciation? There's no evidence of glaciation in the Carson Range. There may be small basins carved by glaciers up near the Mount Rose area, but the essence of the issue is that the Sierran crest acted as a barrier. And so when storm fronts would move up off the Pacific and rise up over the Sierra, they would cool, the precipitation would occur over the Sierra. And by the time they got over the Sierra, there was nothing left in those storm fronts to rain out over the Carson Range. So there was never enough of a buildup of snow in the Carson Range to be preserved over the summer, build up into the next winter, and accumulate to become ice. So the Carson Range has a sort of rounded appearance to it. And that's because the Carson Range has been sculpted primarily by rainfall and landslides, more so than glaciation. The Sierra, a totally different story. The Sierra stole all of the precipitation.
Okay. John Farley has a question. How do you know there were 2 periods of glaciation prior to the Donner Lake period of glaciation if the Donner Lake destroyed the evidence of the 2 previous periods that they had listed?
Yeah, that's a really very good question. And it's a real challenge. The most recent glaciation, the Tahoe, was smaller, was less extensive than the 2 previous glaciations, the Tahoe and the Donner Lake. So there are bits and pieces of glacial till left over from those Donner Lake and Tahoe previous older glaciations. And the way we can tell is it's very qualitative. There's qualitative ways and there are quantitative ways. The qualitative ways we can tell is that the boulders in that glacial debris tend to be much more weathered and rotted in the older glaciations than in the modern glaciations. You could hit it with a hammer and the rocks, the glacial debris in the modern glaciations really ring. It's solid. It hasn't been weathered for very long. But the older glaciations, you hit it and it kind of absorbs your blow. That's because there's an outer rind that's been weathered for longer and longer time periods. Those are older glacial deposits. The more quantitative ways, we use something called cosmogenic surface dating, and we can actually measure the amount of cosmic rays hitting mineral grains, that it's much, much more than I understand and actually have the ability to explain to you. But we can actually date the surfaces of glacial debris and actually put dates on some of these glacial deposits and therefore date the age of that glaciation. But it's a very challenging effort, and it's a very good question, actually.
Great. So 2 technical report questions. So one, is there a report or technical paper that covers this research, and do you have a citation?
Sure. It's a journal that everybody gets monthly, the Journal of Paleolimnology and Paleoceanography. It's a 2009 publication, and I'm the first author. So if you put in Ostlager et al. 2009, this paper will come up. It's in the Journal of Paleolimnology. Limnology, as you all know, are studies of lakes. Paleo meaning study of ancient lakes. So JOPL, Journal of Paleolimnology. When next month's issue arrives at your doorstep, please be sure to read it fully. And
okay, another publication was someone to Adam Ruckert took your class, National Parks class in 2012. Would you have used this textbook, the new textbook, for that class back then?
You know, I'm so sorry. Could you repeat that one more time, Heather?
Adam Ruckert took your National Parks class back in 2012.
Oh, yeah.
Used the new textbook for that class back then.
Adam, I'm thrilled to know that you took my National Parks class. And I took all that information and all those questions you guys asked me back then, and I've kind of used it as the basis for creating this book. And it's taken me forever to create, but it's out now and available. Adam, if you go and buy this book, you know, it's too expensive. Oxford, you know, publishing houses charge far too much for textbooks, so don't buy a hard copy. Go get a digital copy. It's much more reasonably priced. Flip through it and you're going to say, oh yeah, that's what all that was about. That's what I forgot so long ago when I was in college in Dave's class.
Yeah, perfect. So it's 1:06, so I want to close it up, but there is one question that I know you can't answer because it's too big of a question. It requires a whole nother lecture. It is related to how much should we be concerned about the current climate warming? And then another question that talks about global change disorder of, you know, the underlying bigger, larger category. So
huge, gigantic topic. We should all be concerned about it. A whole nother lecture.
Yep, that's what I thought. So, well, thank you very much for your time, and thank you everyone for joining, and have a great afternoon. We really appreciate it, and I will stop the recording now.
Okay.